This video is meant for Mrs. Rose's AB Calculus class, and it is on concavity and the second derivative test. Okay, so things that we want to be able to do when we are looking at functions is this list of 7 things. We want to be able to find critical values, where f of x is increasing and decreasing, where it has relative maximum and minimums, where it has inflection points, where it's concave up, and where it's concave down. So the place that we start for all of this stuff is take the first derivative. So this is an example of where you would use product rule and chain rule, and it's probably a good idea to rewrite this function as x plus 3 raised to the 1/3 power. So our product rule says we have 1 times x plus 3 to the 1/2 power plus x times 1/2 x plus 3 to the negative 1/2 power times 1. Now I'm going to clean it up a little bit. Okay, now that we have our derivative like this, I'm going to get a common denominator so we can find the critical values. To get a common denominator, I'm going to multiply this piece by 2 square root of x plus 3 on the top and on the bottom. And when I do that, we're going to get 2 times x plus 3 all over 2 square root of x plus 3 plus x over 2 square root of x plus 3. So let's make that one fraction. So we're going to have 2x plus 6 plus x over 2 square root of x plus 3, or 3x plus 6 over 2 square root of x plus 3. Now that we have a derivative, we're going to set the derivative equal to 0 and solve for x for the critical values. We're going to set both the numerator equal to 0, so we're going to get x equals -2, and the denominator equal to 0. And here we're going to get x equals -3. So our two critical values are -2 and -3. Okay, so we have that. So I'm going to check off at the list critical values. The next thing I'm going to do is find inflection points. To find a point of inflection, we need to take the derivative of the derivative, or the second derivative. We use our common denominator fraction and use the derivative rule when we have a quotient. So we're going to use quotient rule. The derivative of the numerator is just 3 times 2 square root of x plus 3 minus 3x plus 6 times 2 times 1/2 x plus 3 to the negative 1/2 times 1, all over 2 square root of x plus 3 squared. Okay, so we're going to get 6 square root of x plus 3 minus 3x plus 6 over the square root of x plus 3 all over 4 times x plus 3. Okay, we cannot leave it like a complex fraction like this. So again, we're going to get a common denominator in the numerator. So if I want to have a denominator x plus 3, square root of x plus 3, I need to multiply by the top and bottom the same thing. So we're going to get 6 times x plus 3 minus 3x plus 6 all over the square root of x plus 3 all over 4 times x plus 3 over 1. Okay. Then I'm going to get 4x plus 18 minus 3x minus 6 over square root of x plus 3 times 1 over 4 x plus 3 to get 3x plus 12 over 4 times x plus 3 to the 3/2 power. And the reason for that is we can rewrite the square root of x plus 3 as that to the 1/2 power, and then when you add that to x plus 3 to the 1 power, we're going to get the 3/2 power. Now the whole point of that was to find points of inflection. So to do that, we're going to set our second derivative equal to 0. And again, you're going to look at both the numerator and the denominator. Alright, so these are our points of inflection. Okay, the next thing we want to do is do intervals broken up at our critical values and inflection points. We also need to make sure we consider the domain. So this function has a restricted domain because you can't take the square root of a negative number. The smallest number you can plug in to this square root is -3, and our domain is going to go from -3 all the way up to infinity. So our intervals are going to go from -3 and then stop at our critical value, which was -2, and then from -2 to infinity. You may notice that our points of inflection didn't really make it on there because one's an interval endpoint and one isn't on the right domain. So that's just going to happen, I guess, sometimes, and I'm not really sure what we can do about that. So the next thing we're going to do is figure out the signs of f prime of x and the signs of f double prime of x. And to do that, we need some test values. They can be anything on the interval. So here I'm going to do -2.5, and here I'm going to do 0. And when you plug them into your derivative and second derivative, respectively, you should get positive and negative signs. Go ahead and do that. Hopefully you've got that the derivatives from the interval from -3 to -2 is negative, and from -2 to infinity is positive, and then the second derivative should be positive and positive. So we can make some conclusions based on our little sign chart. Oops, I didn't want to go down that far. Okay, so we know that f of x is decreasing on the interval from -3 to -2, and we know that f of x is increasing on the interval from -2 to infinity. We also know that f of x has a relative. What happens when you change from negative to positive slope? That's right, relative minimum. So we have a relative minimum at x equals -2. We really should find the point though, so we've got -2, and then when you plug in that into our original, let's see, it should also be -2. And then there is no relative max because the derivative never changes from positive to negative. We also can talk about the concavity. We know that f of x is concave up since the second derivative is positive. It is never concave down. So if we go back to the top of our checklist, we've already figured out where it's increasing and decreasing, where it had a relative minimum, and we know it was concave up for the entire function and never concave down. So now we're going to talk about the second derivative test. Like the first derivative test, the point is to figure out what's going on with the relative extrema. If f of x is concave up at a critical value, then f of x has a relative minimum. And if f of x is concave down at a critical value, then we have a relative maximum. That's it for this video. I hope you learned something, and I'll see you in class.